Hi, I'd like to do a little bit of a demonstration of the software packages made available by the French space agency CNES, Centre National d'Études Spatiales. These softwares actually, softwares that they develop and that they use for their own spacecraft design and mission analysis. And I'm going to focus on IDM-CIC, which is what they use for concurrent spacecraft design, right? I'll touch on the mission description software without going in much detail, although it's an important part as well. But this is about the concurrent design aspect. So in this, I start with this slide, of course, made available by the CNES that they were happy to allow me to use, to show a bit of the context of concurrent engineering for some who may or may not know. Right? The context is such that you have all the expertise required to design a spacecraft, right, around the same table. You can see here you have from mission analyst to propulsion specialist to ADCS specialist to power specialist, telecommunications, etc., etc. And they are working on two aspects: spacecraft design and the mission description. You have a software specifically designed to describe the mission concept and mission scenarios, different mission scenarios. And you have this spacecraft, this software designed for the concurrent design of the spacecraft, where every subsystem specialist is logged on, right, to this common project and building his or her specific subsystem such that it all comes together as a whole at systems level, right? I'll show you a bit about that in an instant. On the other hand, there is the design of the mission, and one has to ensure that whatever spacecraft is being designed will indeed fulfill the mission objectives. Why is this done? Because one needs to generate reliable initial spacecraft sizing in terms of mass budget, power budget, propulsion budget, link budget, etc., etc., right? As well as a proper accommodation and the configuration. All right, I'm going to dive right into IDM-CIC. CIC is just the Centre d'Ingénierie Concurrent, which is the French translation of CDF, which is Concurrent Design Facility. So once you are in this, as you can see, it uses Microsoft Excel as user interface, as main user interface for the design of the spacecraft. And it is designed such that at systems management level, you define what, in the context of this software, is called elements. And elements is either platform or payload, or maybe fairing. It depends. If you're going to include the interface with the launcher, you can include it as a separate element, right? But right now we're looking at platform and payload, and you define all the subsystems you will have, and then allocate each subsystem to an element. So you could decide that maybe its structure, you can also allocate it to the payload by clicking on there. Turns green, it means it has been allocated. Or you decide you don't want it to be allocated to the payload, you click on it again. Turns red means it's not allocated, right? This you can do. It allows the systems engineer to define, right, to define all the experts on the software and attribute them specific tasks, right? Allocate specific tasks to them. Forgive my English if it goes a bit weird. And once it's allocated, you will see here I loaded every subsystem here. Each expert in front of their machine will have access to only their subsystem, and they will be able to design this subsystem as they know how. On this interface, you can ask to see, right, and design and fine-tune shapes. For example, you can modify the shapes of the geometry of your subsystem, right? If you don't want to see the shapes, you can ask to see the coordinate systems that you would have defined. This is important, right? You define coordinate systems, you define shapes, you define assemblies, which, putting different shapes together. If you don't want to see this, I'm actually checking the boxes one at a time, because the more boxes you check, the heavier the loading becomes, and I don't have such a powerful machine at the moment. I wouldn't want to overload it. So you can have a look at different power modes, right, by clicking on the power. You can have a look at the mass, right, by clicking on the mass checkbox, and so on and so forth, right? You have a good sense. An interesting thing about the mass is that depending on the level of development of the particular equipment you're talking about, a specific error margin is attributed, right? So if you haven't developed it yet, one will assume you're about 20% out, right? It's good. It's a good margin to go with. So each and every specialist has an interface like this Excel spreadsheet that also gives you the possibility to modify geometries, right? You can have a look at your particular geometry by clicking on this eye that will connect to another software called Sketchup. I'll show you what it looks like in an instant. So, system engineer decided to define all the subsystems, and to allocate a subsystem to each specialist. Each specialist in front of his machine will therefore have an Excel interface that looks pretty much like this, right? To which you could add equipment or assemblies, or you could import, right? You could import from libraries. Why is it great that you can import from libraries, or you can import 3D designs like step files, right? You can import step files from previously designed subsystems. Why is this important? Because you can create a library from your design, and once you have a library, you don't need to redesign the same thing in a next project. You just need to import from the library you would have designed. There is a CubeSat library, very interesting, where you have different subsystems and components and equipments sold by different suppliers that you can import into your project, and this is the case with this particular example here. I'm going to show you the configuration of the spacecraft, right? So once everyone, every specialist has worked on their subsystem, or while they're working on their subsystems, at systems level, one can integrate all of this in here. If there are articulations, you will see them, right? Like different deployment articulations. As I'll show you just now, right? You have here all the subsystems, what they are made up of, where they are attached, right? And their overall position in X, Y and Z. If they are rotated, you add the rotation, and so on and so forth, right? So this is a systems level interface. And what does it look like? What does it look like? If you click on this eye over here, as I said earlier, SketchUp opens and you see what your spacecraft looks like. You can actually turn it around and have a look, at different angles of it. Very interesting to be able to do that. But more interesting also is the fact that you can let me split this right away, so get a good sense of how this happens in real time. So suppose we are in a session, right, in a concurrent engineering session as a team, right? I put this spacecraft view on the big screen somewhere, right? See, there's a camera inside and stuff. And we try to see what happens if we attempt to deploy the solar panels, you know, to say 80 degrees, and you see they open, right? They open. Okay, that works. Let's see what happens if we try to deploy the antennas, right, all the way to 90. And this takes a bit more time because it's a long chain of articulations, but you will see that the antennas, it's actually UHF and VHF antennas, right, off the shelf, that then deploy, as you should see at any moment now. Unfortunately, this computer is not the most powerful on Earth, so there we go. So you can have a look, you know, simultaneously, and each and every one can see where their subsystem is, you know, and how it affects the others. You can actually, using this visualization tool, decide to filter out what you want and don't want to see. Suppose we remove the entire structure, right, by clicking here, right? You see how responsive it is. You can have a look inside, right? Have a good idea from a design point of view. Everybody sitting together, making sure nobody is going off the rails. We can decide we want to not see everything comes and it all disappears, or we bring it back and everybody is happy. If we don't want to see the payload goes away, the camera has gone away, and then we bring it back. You know, these are some of the things you can do, right? Working as a team on the same project, right? Okay. Once you have this configuration visible, what you can do also is to view it in IDM view. IDM view is a visualization software, right, that allows you to sort of manipulate, see a little bit the articulations, look more in depth, you know, into the spacecraft. And in there you can really do some interesting things like, unfortunately, again, because this machine is not powerful, I extracted beforehand a little animation that should allow to see what you can do with IDM view. If I can find it right here in demo. Fantastic. So in IDM view you can generate an animation like this one, which basically shows you, you know, it allows you to display different aspects and mechanisms of, you know, in here you can do much more than this. You can, after this, you can decide that you want to obscure some parts, you want to have the structure a bit transparent to see inside, and so on and so forth. And here you get to see which are the heavier parts and how each mode behaves with respect to the mission. What do I mean? All right. Right, looking at the power budget from a different model, you can see how it actually works. So because each subsystem defined the power modes, here we defined what the platform does, you know, in different modes. So the platform can be off. Now if the platform is off, What does it mean for each subsystem? So when the platform is off, for example, how is the EPS doing? What's the power system doing? Is it off? Is it on? If what's the ADCS doing? Everything is off at the level of the ADCS, and so on and so forth. When you have this the platform in, for example, if there's a silent mode, what does silent mode mean? It means that the EPS is on silent mode. It means that ADCS is on safe mode, and so on and so forth. So this is a simple allocation that can be done at this level, and then you get the system power budget, which means you basically allocate power modes per the system, the entire satellite. So we were talking before at element level separately what is the platform doing and what is the payload doing, right? Now you define system modes that need not be the same as element modes. So the satellite can be off, it can be detumbling, it can be, it can be silent, deploying, and so on and so forth. That corresponds to power modes that can be chosen. If you choose the element mode, that you defined previously, you just allocate it because you've already done all the definition in the previous sheet, right? And this is how you really get the entire power budget, right? You can generate the full power budget this way, right? It's extremely important because then you have a good idea about your mass budget and your power budget. I'd like to shift to one subsystem, right? I'll just go with this one and show you what I was telling you about the CubeSat library. So suppose this is telemetry and telecommand, right? Suppose I want to import. I want to import something I've already done before. What can I import? I can import 3DS, or I can, since we're talking about the CubeSat library, I can import, here you go, this is the CubeSat catalog here. You can pick from different subsystems. Right now we're talking TT&C, so it would be, for example, communications, right? But if it were ADCS, you could pick from ADCS, you could pick from power and so on. Power, you can pick solar panels and things like that. Here, if I open it, when it decides to open, of course, there we go. We start seeing what is in the library, right? You get some from GomSpace, you get some from ISIS, and so on and so forth. I think it would be interesting to see. There we go. This is the CPUT S-band antenna actually there, right? And you can import it. If I decide to import this antenna in here, it becomes part of my model, right? And I imported, it was designed with all its rating, its mass, and so on and so forth. And then it becomes part of my spacecraft. I just need to go to the configuration that I showed you before and position it accordingly, right? So here it is over here that I just imported. It says here Clyde Space CPUT S-band antenna. Is it hidden? No, it is an equipment, and so on and so forth. And you can have a look at the shapes like I showed you before, and you can also take a look at this directly in Sketchup. It's going to open Sketchup as I told you before. There we go. So we have here the IDM model of the CPUT S-band patch antenna, and we can turn it around. It's a very simplified model because at this level, at initial sizing, you really don't need to get into the high level details because you can always export what you do here all the way into CATIA if that's what you're using, or SolidWorks if that's what you're using, and then, you know, get into a higher level of detail of the definition of your particular subsystem from a mechanical point of view, of course. All right. So I have spoken about the system configuration, how the systems engineer can allocate different tasks. I have spoken about the interface of each specialist, and how whatever they're doing at their level, how it all comes together, you know, at systems level. I showed you a little bit of what you can get when you export it to IDM View, the kind of visualization you can have of your 3D model. Now I want to touch a little bit on, once you take a model developed like this and you place it into the description of a mission, right? Here what you use is something called VTS, which is another CNES software that you use. It's similar to STK, right? But it works hand in hand with IDM-CIC and also CMU-CIC. So here you get a view like this, where you basically have your mission timeline and you can add different events along the line, right? And the graphic rendition looks something like this, where you can have a surface view and you can have a 3D global view, a bit like this one, right? On which you can zoom in and out and, you know, shift the view to have a better perspective. I'm not going to play it here because it's a bit glitchy on this very weak and poor computer, but I will show you something that I have done previously for this very mission that you're looking at. So, all right. So imagine that you have a spacecraft that, as you see, when it comes inside of the ground station in Cape Town, switches on its antenna and acquires some instructions, you know, to gather some data from ships in the South Atlantic near Cameroon, and then get some images of the capital city, Yaoundé. This is a simulation that this is a mission that I simulated for demo purposes, and it shows the kind of visuals that you get from VTS, right? So this is the spacecraft actually acquiring the images that were asked from it. And you can see in the yellow arrow the direction of the sun, and on the left hand side you have a surface view, and on the right hand side you have a global view. I just want to finish off on this slide on which I started to just mention one last thing about concurrent design facilities, that it doesn't have to be a physical place, right? It could also be a well-designed network, right? And still work with these softwares. It doesn't have to be a physical place where people need to move to be there. One can do effective concurrent design with people placed at different places around the globe, and it does happen that way. Sometimes for security purposes there may be a need for being in a specific location, but if you have solid cyber security measures in place, you can also mitigate that. Thank you so much for your attention, and I look forward to any questions you may have about this particular presentation. You can just get hold of me. Thank you very much.